All right. Day 2 for chi-squared. What we do is very similar to what else we did this chapter, which is start with some kind of point estimate for whatever you're looking for, and then find some error, and you go up and down that amount, and it will give you a confidence interval. And we'll probably stick with the main ones like 90, 95, and 99, but we can't use Z or T because this distribution is completely different. Okay? And that's why I tried to start off with day 1 very simple with chi-squared to show you that it's a distribution that, remember, it kind of starts from here, goes up, and then goes forever that way, correct? And as your degrees of freedom, or n, gets bigger, the more and more it looks like a normal distribution, okay, and the more it changes. Okay? So if degrees of freedom is really low, it might be something like that. Or as the degrees of freedom get larger, it starts looking more and more like that. But the reason we don't have to worry about negatives is we are actually working towards variance is what we're looking for. Because let's face it, if we can find the variance, we can just take the square root and we've got standard deviation. Okay? And so chi-squared helps us. That distribution that they came up with seems very arbitrary, right? It's like they just made something up. Okay? Hopefully today, after we go through this, you can see that really they reverse engineered that. They knew what they needed, and they made it that way. Okay? All right. Got a slight interruption there. Thank you for your patience. So again, that distribution they gave us, it was basically engineered to give them what they needed. Okay, I'll give it to you this way. Sigma squared's in there. We need to be able to get it out. It's as if they've hidden it in there, because it's the only way they could get it there so that you could do it by hand. Otherwise, we could do it via calculus, but I'm assuming that you probably don't want to do it that way. Okay. So if we're trying to find a point estimate for sigma squared, what do you think is the best point estimate for that? Again, we're trying to use some sample. What could I take from that sample that would probably be pretty close to sigma squared? S squared, right? Which is the sample standard deviation, or sample variance, excuse me, is what that would be. How about a good point estimate then? Again, we're trying to find that it may be right, it might not be, right? And then we give the interval from there, right? So what would be a good point estimate for just sigma or standard deviation is just S, right? I mean, we're not going to go find the mean if this is what I want, right? We're not going to go find the median if I want standard deviation. We'll go find the standard deviation of that sample. And that should make sense. That's what we've done this whole time. When we looked for the mean, we found x bar. When we wanted proportions, we found p hat. Okay? I mean, we're finding the best we can. And we talked about this yesterday. The actual distribution is made by that function. And as n, s, and sigma change, is the distribution going to change? Yeah, we just said as n gets bigger, it gets more and more like the A normal distribution, right? As n is small, it's not very much like a normal distribution at all. And so we can't use the central limit theorem on this. It's not going to help us out. Right? And that's why they had to come up with a whole new distribution, and they called it chi-squared. Again, they kind of hid sigma squared in there. Okay? So is everybody clear that as these variables change, the look of that graph and the distribution of the values will change? Is everybody clear on that? Yes, no, maybe? All right. So that's what the distribution actually looks like. And if we were using calculus, we would have to use this function, okay, which looks like lots of fun. So we're going to find critical values for particular degrees of freedom. That's what you get in that table, right? That's what it tells you. If I told you, like earlier, we just did a couple on the homework. If I give you degrees of freedom and how confident I want you to be, can you find chi-squared right and left? Okay, some of us need to work on that a little bit, but hopefully we'll be able to get there, right? Those are going to be the very important values, because in those values is sigma squared. Okay, it's in there. All right? We have to be able to get it out. So here's how we're going to find this. This is kind of lengthy, but then the second one, you're probably not going to have to write all that much, okay? Because once you write this first one, you're pretty much going to have what you need. So if I want to find sigma squared, notice that's where it is. I want to estimate for this. This is kind of like the interval, like we've been doing it like that, right? There's going to be this number would go here and that number would go there, right? Sure, I can make that bigger. Because there's a lot of information in there, a lot of subscript and whatnot. That's better, I hope. So over here, to find the left endpoint of the confidence interval, I would take n minus 1 times s squared and divide by chi squared right. Well, that's weird. How come chi squared right's on the left-hand side? That's weird. But do you agree in all of these, chi squared right's going to be the bigger number because the distribution fills from the right? And so does it make sense if I take something and divide by a big number that it's going to actually be smaller than the other one? Okay. And then over here it's n minus 1. It's the same thing on top for the left hand, or for the endpoint on the right, but I divide by chi squared left because it is the smaller of the two. And that's the only unfortunate thing about this distribution, is that it fills from the right. Okay? Because it has to. So if we could get that information, meaning if I could get this number and that number, what do I have to do to those numbers to make the interval over here for sigma? I just have to take the square root, right? So you can write this whole thing over here if you want, but really, do you notice all I did is I took the square root of both of those numbers, right? That's all I did. Because if you take a look at this, it's just right inside that square root. So if you just want to make yourself a note, oh, just take the square root of that, it's fine. And then also notice this one had the square root taken as well. So really, chi squared is much more for variance. And I really believe that's why they didn't just call it the chi distribution. They called it the chi squared, so that squaring was in your mind, so that you knew it was variance, because that's the squared of standard deviation. Now, this may or may not go as well as I want it to, but we're going to try it anyways. So those listening to the recording, you can decide if you want to listen to this or not. But this is going to show you how variance, or sigma squared, is actually in that distribution. Because where would I get that number from? Do you agree that's a number? I get it from that table, agreed? It's a number that I find by knowing degrees of freedom and confidence, right? That's where I'm going to find that number from. So let's just do some math here. Let's do some algebra. So here's the here's the numerator, right? Of what they want me to do. That comes from a certain distribution, doesn't it? What distribution does that come from? It comes from right here. Agreed? So that's how I really am finding that value. So let's write that. That's really what my denominator is. So let's write that in the denominator. Agree? To figure that out comes from this distribution, right? That's what that table's made from. That's how they made the table, was from this distribution that's in the denominator now. So wait a minute. Here's kind of where the real division happens. So I can multiply by the reciprocal of this stuff at the bottom, right? So this just goes here. Watch this. And I can make that over 1, right? I think somebody said to do that the other day. That'd be helpful. Let's multiply by the reciprocal of this. Does anything very advantageous happen when I multiply by that reciprocal?
They cancel.
What cancels? N minus 1 cancels. S squared cancels. And I'm left with not O squared, it's sigma squared. So that's what I mean. Sigma squared is hidden within that distribution. And if I substitute it into here, everything else cancels and leaves me with sigma squared. So they engineered that distribution by knowing what did they need to put here so that sigma squared was the only thing left over mathematically. Okay. And do I really need to know a lot of information? I need to know N. I need to know S. And there's only one more thing I need to know to be able to do this. Well, we have a whole lot of letters going out, and none of them are right. I need a confidence interval. Okay. So let's try one. I know for some of you this kind of went maybe over your head a little bit, but that's really where sigma squared's in there. We just have to get it out. So let's try one. You randomly select and weigh 30 samples of an allergy medicine. The sample standard deviation, and let's face it, if I don't know that, we have to go find that. And how would you find that? If I gave you a bunch of data, how would you find S? You would go to the graphing calculator and it would tell you. Okay? The sample standard deviation is 1.2 milligrams. Assuming the weights are normally distributed, construct a 99% confidence interval for the population variance and standard deviation. So am I actually going to find the population variance? No. Am I actually going to find the population standard deviation? No. Because is there any way for me to get all the allergy medicines in the world? Probably not. So we're going to construct an interval to try and get close. So what are some things we know? In this problem, 30 must stand for something. 1.2 stands for something. And is 30. S is 1.2 because it is the sample standard deviation. Correct? Okay. Confidence, or C, is 0.99. Do we need anything else? Yeah, I'm going to need chi-squared right and left, but that's something I'm going to have to go find, right? So let's find chi-squared right, chi-squared left. Because what information is in there? In chi-squared right and left are my sigma squareds. It's in there. I got to get it out. So, uh-oh. There it goes. I have once again gone to my graphing calculator and given you what the actual distribution would look like graphically. Did you notice N got pretty big in this one, didn't it? So look at that distribution. It looks very much almost a normal distribution, right? And now notice how far this value goes out now, 55, right? Yesterday, didn't it only go up to like 15 or something like that when we did that? So you notice there's a lot more going on with this one. So I chose degrees of freedom of 29 down here, right? Everybody see that? Because N was 30. And now we got to figure out, we need basically, in the distribution, we need 99 in the middle, right? Which means how much on each side? Well, basically 0.5%, right? Otherwise known as 0.05. So as it fills from the right, I should look for 0.00. Yeah, easy with the O's. So if I'm at degrees of freedom of 29, here's 0.005, so the chi-squared is 50, I can't read it now, is 52.336. Which one is that, chi-squared right or left? Right, so it's 52.336. So apparently, sigma squared's in that number somewhere. Somehow I got to figure out how to get that out. So down here, chi-squared left. Well, how do I do that one then? Well, yeah, you got to figure out how to go all the way across, and so that would be 0.995. And again, so it's right here, that number. So that's 13.121. Now this makes sense, because who can tell me what's the mean of this distribution? Not that I really need it, but what's the mean of this actual distribution? If you can remember from yesterday. 29, good job. The degrees of freedom is your mean. So do you agree 29 should be right about in the middle? Yes. The mean will always be the degrees of freedom, yes, of the distribution. In a chi-squared distribution, yes. And it's not chi, it's chi. All right? All right, so now we have to go and find what that is. So let's go find our interval. So our formula says, that will tell me the smaller number. That'll tell me the larger number in the intervals. There's a lot. Okay. Oh, here we go. N minus 1. 29. I'm running out of room, though. We're going that way, and we're going to erase this distribution over here. Because we all figured out that part. So we got 29. What's S? 1.2, but we're talking about variance, so I better square that. And it turns it into the sample variance, right? Over Why is it over chi-squared right again? Because it's going to be a bigger number I'm dividing by then, right? Which will actually end up giving me the smaller of the two values. Agreed? Because the numerators are the same, right? And so divided by 52.336. Here's what I get. This numerator, this 29 times 1.2 squared, is in this calculation for 52.336, right? So if I cancel that out, the only thing left is going to be sigma squared. Everything else is going to cancel for me. But this is how they had to do it, so I could do this by hand. All right? And so what number do we get if we do all those calculations? I'll go ahead and, oh, does somebody already have it? Oh, well. 0.798. I wasn't ready for somebody to have that already. So then over here, for the larger number, you notice the numerator, the same. Over now, chi-squared left. I know that's weird that you put them under the wrong ones. It seems like you're putting them under the wrong ones, but the numbers come out, right? And so we get what? 13.121. 3.183. Yes?
So how much say we stop it? Can we just kind of
Oh, good question. The question was, why did we stop yesterday at just chi-squared right and chi-squared left? Because chi-squared is completely new to all of you. It's a completely new distribution. You're not used to looking for it. You can find the mean. You're used to finding that. You're used to finding proportions, but not used to finding chi-squared. Completely new, so I wanted to make sure we could find those things first.
so that was just like that. Oh, so they're just the values of that. That's not the actual.
Exactly. What somebody just said is those are just the values that help me find the interval. They're not the interval themselves. Exactly. Perfect. These are the numbers that are these are the numbers hiding sigma squared on me. They're hiding it. So here's my interval for what? 0.798 to 3.183 is the interval for which population parameter? What is it? Sigma squared, in other words, variance. Okay. So now, what do I do to these numbers to get standard deviation confidence interval? Square root them. Now this number is less than 1, so actually the square root of that's going to make it bigger, actually. That's kind of strange, right, for a square root to get bigger. I'm not sure we needed the dance move there. 0.89, and this one will actually get smaller, and 1.78. So do we actually know the population standard deviation? No. But how sure are we that it's between 0.89 and 1.78? We're 99% sure. Yes? Oh, okay. This one here is for variance, or sigma squared. Okay? So to get standard deviation, I just take the square root of these numbers and put them down here. This is for standard deviation, or just sigma. Okay? It depends on what were we actually asked for. They wanted both. Yep. But which one of those two is more helpful to us in calculations is the standard deviation, because it's the same units, right? Variance is squared units, and that's not what we want, right? But variance helps me get to standard deviation. Okay? And it was easier for them to make a distribution that dealt with variance than it was for standard deviation. There would be more dividing involved if it was for standard deviation. So they went with the distribution that was easier to do that. Easier to hide the answer, basically. Does that help? Okay. That was weird, right? But very creative on their part to engineer this the way they needed it. They came up with what they needed. Very clever. So let's construct the 90% and 95% confidence interval for the population variance and standard deviation of the medicine weights from example 1. It is. So what's n? Did that change in the span of the last 10 minutes? No. It's, wait, I wrote 10 for some reason, but it's 30. No, I was just thinking of the other example. I wish I was keeping you on your heels, but I just messed up. What's that? What did I say? Oh, did I? I don't know. And what else do we need? S? 1.2? Again, what if you don't have S? Go get it. C, let's just do 0.90 first. And something else that's helpful is degrees of freedom. You can remember that's the amount of numbers that can be whatever they want to be, right? And that's 29. So if I'm going to try and get variance out of that chi-squared distribution, I need chi-squared right and left. Because that's really where the number is hidden anyways. So I need those two values. It's just them being very sneaky. So there's your distribution again. Again, looking very much like a normal distribution. On the left-hand side, remember over here, it does touch. On the right-hand side, it actually does not. It does keep going on forever, which is why, unfortunately, they have to fill it from the right. So chi-squared right. So notice degrees of freedom. I did give you 29 again. So now we have to figure out which value should I be looking for. And I need how much in the middle? 90 in the middle, which means 5 on each side. So this time, do I look at 0.005 again? No, just 0.05, correct? So again, if you're filling from the right, we're just going to look at 0.05, which apparently is that number, which is chi-squared right or left? 42.557. Chi-squared left then. We have to know which value we're looking for. So we have to get basically all the way over to that spot, wherever that happens to be. We've used 5% up and then another 90, so 0.95 we're going to look for, right? Which is so it's strange that in this case our chi-squared right actually got smaller, our chi-squared left got bigger. In the final calculations, is that actually going to work out for us if we're going for 90% sure? Yeah, because what's going to happen to our interval? It's actually going to shrink, right? If we only want to be 90% sure. So now we have to figure out how to do that. How do I divide on this side? To get the smaller number, I divide by chi-squared right, because it's the larger of the two, right? And over here, this is the stuff I'm basically canceling out, which is what this numerator is. That's chi-squared left. So yeah, if we move over here again with our calculator, we got 29 times that 1.2 squared again, right? Over, this time 42.557. And then this is really the stuff, again, I'm canceling out whatever that number is. And I'm divided by 17.708. Sorry that my comma got really disproportionate to the rest of the problem there. So that's a 7, and this is a 17. I'll put my comma down there, I guess. And if I do this calculation, what answer am I getting? Confidence interval for what? Variance. A 90% confidence for variance. What is it? 0.981? For the lower, I'm assuming, right? And? I think it's 5, isn't it? Yep. No surprise, this first one's going to almost be the same number because it's almost 1, and the square root of 1's 1, so this has got to be pretty close to the same thing. 0.9? 0.99, okay. 1.536. No, he didn't. So this one is for variance. That's for standard deviation. Now please realize, though, this is also based off of one person's sample. It's very possible that somebody else could go out and find the sample sample standard deviation was 1.3. And then that's going to be a completely different distribution and coming up with completely different answers because their S is different. Okay. Well, their intervals are going to change, but that's why we're only 99% or 90% sure that we caught the answer. Because that person's sample could have been terrible. But that's why we're widening our range to hope we catch it. And again, 90% means that if 100 different people went and got samples, 90 of those samples, if they all followed the same rules, would actually catch the answer. 10 probably would not. Okay. Your homework for tomorrow is to do, or for Monday, in this case, is to do the 95% confidence interval for this problem. How should the 95% confidence interval relate to these two? Should it get bigger or smaller? A little bit bigger, right? So it really should be between this one and the one we did before, right? Because that's 99. So, good.